Hi everyone. In this video I want to talk a little bit more about finding the domain of a function that's given by a formula. So we should be able to, after doing a little bit of practice here, look at a whole lot of different types of functions represented by formulas and identify the physical domain. So this isn't about word problems. In word problems, you'll have to ask yourself what makes sense in the context of the problem. This is just about looking at the formula and deciding if there are any values that you should not plug in. So we're just going to jump right into examples. All of these, I just want to find the domain. Sometimes it's fairly easy to also reason your way through the range, but for the most part, we'll take range more as a graphing question. So we'll be working a lot this quarter at looking at functions given by formulas and learning how to figure out what their graph looks like just by looking at their formula. And as we get better at that, we'll get a lot better at identifying range as well, just by thinking about the picture of the function in our head. Okay, first one. A of x. A of x is equal to x cubed minus 1. So really what this boils down to is it's almost always easier to ask yourself, instead of what am I allowed to plug in, what am I not allowed to plug in? So you want to be thinking about only real numbers. If anyone's worked on imaginary, we are not doing imaginary numbers in this class. So do not even worry about that. So if I'm thinking about any possible real number, is there something that I could get in trouble with if I tried to cube it and then subtract 1? And basically here the answer is just no. It doesn't matter what kind of number you give me. So make sure you're being really broad in your thinking. We do not want to be restricting ourselves to thinking about positive integers. X could be a positive number. It could be a negative number. It could be a fraction. It could be an irrational number. It could be pi, the square root of 2, something like that. It could be a really, really big number. It could be a really, really tiny number. Maybe x is 0.000003 or negative 0.00000006. We don't want to forget about any of these possibilities. So thinking of all the things you could do, there is not a single real number out there that I can't figure out how to cube. I can always take whatever kind of messy number I'm working with and multiply it by itself. No problem. I can do that a couple of times, still no problem. There's also not a single real number out there that I can think of that I'm not allowed to subtract 1 from. That's always legal. Sometimes people worry a little bit about if x is 1, I get 1 cubed minus 1. 1 cubed is 1, so I get 1 minus 1, which is 0. That is no problem. Getting 0 doesn't mean you didn't get an output. It means the output you got was 0. 0 is a completely acceptable output. It's not the absence of an output. That would be empty set. It is your output is 0. So for this function, the domain is all real numbers. Feel free to write it out in words if you don't want to try and remember any more symbols, but I'm all about having shorthand where it's not terribly inconvenient to try and remember them. So the boldface R means all real numbers, and you are welcome to use that. I would say that's the set notation version. That's the set of all real numbers. The interval notation version would be we want everything starting from negative infinity and going to infinity. In case I haven't said this yet, we always give infinity round brackets. The idea is that you can't actually get to infinity, so you can't really include it in an interval. So anytime you're using an infinity or a negative infinity, it should get a round bracket. So there's actually a lot of the functions that we work with right now will have a domain of all real numbers. Linear functions, always going to have a domain of all real numbers. All of our quadratics, in fact, any polynomial, so any function that involves adding and subtracting terms who have variables with positive integer powers, that sounds really complicated, but basically quadratics, cubics, fourth degrees, all of those have a domain of all real numbers. Okay, let's look at another one. B of x is equal to 3x over 2x plus 1. Okay, so same question. Instead of saying what am I allowed to plug in, it's usually easier to figure out what you're not allowed to plug in. So I have quite a few operations here. whatever my input is, I'm going to have to multiply it by 3, and I'm also going to have to multiply it by 2. In the bottom, I'm going to have to at some point add 1 to whatever I'm working with. And then the last thing that happens here is I perform a division. So a lot of those steps are just like up above. I can multiply any real number by 3. There is not a number out there that I can't multiply by 3 or multiply by 2. There is not a real number out there that I can't add 1 to. So mostly I'm not having any problems with any of these steps. I can plug in whatever I want. There is one step I can have problems with though. Division can be a little tricky. You don't want to divide by 0. So there is a single problem to worry about here. I do not want to divide by 0. Which means I want to make sure that the bottom of this thing, the 2x plus 1, is not equal to 0. You can set this up and actually solve it. So if you can look at 2x plus 1 and figure out the x value that makes it 0 without showing me any work, do it. I think that's wonderful. But if you find yourself getting your fractions upside down or switching your signs, go ahead and do the algebra. If I want to make sure that 2x plus 1 is not equal to 0, I need to make sure that 2x does not equal negative 1. And that x does not equal negative 1/2. So again, if you can look at this and say, I need to make sure x is not negative 1/2, make sure that's still a not equal to, that's fine. I don't need to see these steps. I should be able to plug in anything else I want to. There is no other x value that will make the denominator 0. There's no other reason for me to have a problem performing any of these operations. So this really is the whole domain. If we want to make it a little more formal, tack on some set brackets. We can say the set of all real numbers x such that x does not equal negative 1/2. If you prefer interval notation, I want everything from negative infinity up to negative 1/2. I want to make sure I leave out the negative 1/2, so I'm going to give it a round bracket, and then I'm going to start up again and go from negative 1/2 to positive infinity. So I don't need to see both of these. One or the other is great. You should recognize either one. You should know what I'm saying if I write down the first or the second, but you can just give me one of the two and I'll be fine. I'm even fine if you don't include set brackets and just tell me that x is not equal to negative 1/2. I do want to make sure that you're really clear that when you say x does not equal negative 1/2, what you're saying is x can be anything but negative 1/2. So if you want to leave out something else, make sure you write that down as well. Okay, let's try c of x is equal to the square root of x plus 3. Okay, so same question. Can we identify the domain of function c? Function c really only has two steps, two operations happening. Whatever I input, I'm going to add 3 to it, and then I'm going to take the square root. I can add 3 to whatever I want. We've already talked about addition, subtraction, multiplication. There's not really any way to get in trouble performing any of those operations. But there are some things that give me trouble if I'm taking square roots. Again, I want to be really clear that this class is about real valued functions. So we're not talking about inputting or outputting imaginary numbers. So for our purposes, if you would end up with an imaginary number, then we would say you're not ending up with an output at all. We only want to get real value outputs. So here, it's a little different than the last one. What I want to make sure of in this case is that x plus 3 is greater than or equal to 0. So if you have a fraction in your function, you want to make sure the denominator is not equal to 0. If you have an even root, a square root, a fourth root, a sixth root, you want to make sure that whatever is trapped under the root is greater than or equal to 0. It is completely fine to take the square root of 0. The square root of 0 is 0. We're only in trouble if we have negative numbers. So we want to make sure that the thing under the square root is not a negative number. Again, you can solve the inequality just like an equation. The only thing you want to remember is that if you end up multiplying or dividing by a negative number with a directional inequality like this, it will switch directions. I don't think we need to worry about that here. We'll just carefully do this so that we don't end up multiplying or dividing by negatives. We subtract 3 and we're done. So if we want to make sure that we are allowed to take the square root of x plus 3, we're going to make sure that the x that we're starting with is at least negative 3. If we start with negative 3, we get the square root of 0. If we start with something bigger than negative 3, we'll get the square root of something bigger than 0. So again, just this as a domain looks great to me. If you want to be a little formal, you can throw on some set notation, say the set of all x such that x is greater than or equal to -3. If you prefer to use interval notation, this one we want to start at -3 and go to infinity. -3 gets a square bracket here. We want to include -3. Remember, with interval notation, you always need to write those out smallest to largest. So order does matter with the interval notation. Okay, I think I'm going to quit here for this video. I'll put some other examples in another video. Thanks for watching.